Have you ever gazed up at the night sky at the countless pinpricks of light representing distant stars, galaxies, and felt an overwhelming sense of distance? The universe is unimaginably vast, so immense that even traveling at the speed of light would require thousands of years to reach our nearest stellar neighbors. This cosmic speed limit seems to condemn humanity to our tiny corner of the Milky Way. But what if there were a loophole? What if there were a secret door? A hidden passage through the fabric of space and time itself? This is the tantalizing promise of the wormhole, a concept that has captured the human imagination, fueled our wildest dreams of interstellar travel, a shortcut through the cosmos. This idea, however, often gets lost in translation between the chalkboard of theoretical physics and the silver screen of Hollywood. Cinematic depictions show us gleaming, stable vortexes, sleek starships zipping from one galaxy to another in the blink of an eye. The reality, or rather the theoretical possibility, is far more complex, more dangerous, and infinitely more fascinating. To truly appreciate the concept of a wormhole, we must embark on a journey of our own. We must carefully peel back the layers of myth, science fiction, to reveal the beautiful physics, perplexing physics, still unproven physics that lies at its core. It is a quest to separate what is merely plausible from what is truly possible. The discussion of wormholes is not just an idle fantasy. It represents one of the most profound inquiries in modern science. It pushes the boundaries of our most successful theory of gravity, Einstein's general theory of relativity, to their absolute breaking point. The equations that govern the cosmos, the very same ones that predict black holes, the expansion of the universe, also contain within them the mathematical seeds for these extraordinary cosmic bridges. To understand a wormhole, we must first reimagine our universe. Do not think of space as an empty void, but rather as a dynamic, four-dimensional fabric called spacetime. This is the central lesson from Albert Einstein's general theory of relativity. Massive objects like stars and planets do not pull with a mysterious force. Instead, they warp and curve the very fabric of space-time around them, like a bowling ball on a trampoline. Planets then follow these curves, which we perceive as the force of gravity. A wormhole, in this analogy, is not just a hole in the fabric, it is a profound topological feature, a tunnel connecting two different regions of that same fabric. The formal name for this structure is an Einstein-Rosen bridge, first proposed by Albert Einstein and his colleague Nathan Rosen in 1935. They were exploring the bizarre mathematics of black holes and discovered a solution that suggested a black hole could be connected to a white hole, a theoretical object that spews matter out. This created a tunnel-like connection. Imagine marking two distant points on a sheet of paper. The shortest path is a straight line, unless you fold the paper so the points touch and poke a hole through, creating a dramatically shorter path. This is the essence of a wormhole, a shortcut through spacetime. This theoretical leap is truly astounding. It suggests the immense distances between stars and galaxies might be an illusion of perspective. The journey from our solar system to the Andromeda galaxy, a trip of 2.5 million light-years, could be reduced to a manageable stroll if a traversable wormhole connected the two. Furthermore, because space and time are inextricably linked in relativity, a wormhole doesn't just connect two points in space. It could also potentially connect two different points in time, opening the possibility of time travel with all its paradoxes. However, the initial Einstein-Rosen bridge had a fatal flaw. It was dynamically unstable. The throat would pinch off so quickly that not even a single photon, the fastest thing in the universe, would pass, a bridge collapsing the instant you step on it. The movies make it look so easy. A starship approaches a shimmering anomaly. The captain gives a command, and with a flash of light, they are instantly transported across the galaxy. This popular portrayal has cemented several powerful myths. The first myth is that wormholes are natural, stable phenomena, just waiting to be discovered like planets or stars. The science suggests the opposite. There is currently zero observational evidence that wormholes exist anywhere in the universe. We have found black holes, neutron stars, and other exotic objects predicted by relativity, but wormholes remain entirely theoretical, a ghost in the mathematical machine. Another myth is that we are on the verge of building our own wormholes. This is pure science fiction for the foreseeable future. To overcome fatal instability, physicists like Kip Thorne proposed propping the throat open with matter that has negative energy density. Gravitationally repulsive exotic matter. Tiny, fleeting negative energy can be created via quantum effects like the Casimir effect, but we have no idea how to produce or stabilize it in the vast quantities needed for a macroscopic wormhole. Perhaps the most dangerous myth is that wormhole travel would be safe. Even if stable, the mouth would have extreme tidal stresses. Those forces could tear a ship, and any person inside, into constituent atoms. The tunnel would be a maelstrom of high-energy radiation and virtual particles, amplified by bizarre curvature, like being fired through the heart of a particle accelerator. So, where does reality lie? Wormholes are valid mathematical solutions in general relativity. They are not forbidden by known physics, which is tantalizing. Exotic matter is a major hurdle, but it doesn't close the book on the idea. We may need a more complete theory uniting gravity and quantum mechanics to understand if wormholes can form and persist. The reality, a profound theoretical puzzle, not a practical ride. Despite the immense challenges, scientists have not given up on the idea of wormholes. The pursuit is driven not by building a starship tomorrow, but by the desire to understand the fundamental laws of the universe. Current research is primarily theoretical, on supercomputers and blackboards, seeking stable solutions that might need less exotic matter, or perhaps none at all. They explore how wormholes might behave, predicting observable signatures. Relativity rules the cosmic, quantum mechanics the subatomic. These pillars conflict in extremes: the center of a black hole, the throat of a wormhole. A unified theory, string theory, loop quantum gravity, may reveal if wormholes emerge naturally. Observationally, astronomers keep watch. Unique gravitational lensing, wormhole mouths bending starlight differently, perhaps twin images of the same star, or orbits around an invisible point with no detectable mass. So far, no definitive evidence. The investigation also probes energy. The main obstacle is exotic matter and negative energy density. Labs study the Casimir effect, two plates in vacuum, creating a region of slightly negative energy. It's far from opening a gateway, but proves negative energy isn't just math, a measurable quantum phenomenon that keeps hope alive. In the final analysis, are wormholes real? The honest answer, as of today, March 3, 2026, is that we do not know. They remain compelling and speculative. We have no direct evidence. The requirements to create or sustain one are far beyond our current science and engineering. Stable, traversable wormholes of fiction are, for now, fiction. Yet dismissing them is a mistake. Our mathematics, like that describing gravitational waves and black holes, unequivocally allows them. They are a legitimate possibility, pointing to gaps in knowledge and the need for deeper quantum gravity.